Hi everyone. Sorry for being so late with the lecture. I kind of planned to give this during the quiz, but as we saw, it wasn't really possible. And in future, I did decide that I'm not going to give any lecture when we have quiz. I hope you all did well. I think quiz was not hard at all. So this was probably the easiest one. We'll see in future, but I will try my best to facilitate your learning. Now, in terms of this special lecture that refers to the unit 3, which is functional diversity of microorganisms, so, I have only a few slides that I wanted to share with you, and most of these things you already heard in our previous lectures, but there are some new things that I would really like you to memorize, and I will include it in our next quiz and on midterm. So, we already covered ammonia oxidizing bacteria or AOB and methane oxidizing bacteria MOB. So you should all know what those organisms are doing so far. But today I will talk a little bit about evolutionary connection, just briefly, that exists between those two groups of organisms. And I will touch base with evolution of nitrogen cycle, which is one of my favorite biogeochemical cycles. Of course, if you have more questions and you would like to learn more about nitrogen cycle, I would be very happy to answer questions. It is one of my favorite topics. So briefly, just brief recap, nitrification is a process that can be done either by AOB or AOA. AOA means ammonia oxidizing archaea, and it's usually done in combination with nitrite oxidizing bacteria or NOB. So basically those two groups of organisms would complete full nitrification from ammonia to NO3 minus, which is nitrate. And the second group of organisms, this one is only one group actually called COMAMOX. So they are also doing complete nitrification, but they have all enzymes and to convert ammonia to NO2 minus and NO2 minus to NO3 minus. And that's basically done with AOB or AOA and NOB in combination. Now, nitrification is known as aerobic process, which means that oxygen is used as terminal electron acceptor, so they respire oxygen, while opposite process of nitrification is called denitrification, that we covered as a part of anaerobic metabolism, because NO3 minus is a molecule that is a compound that can be respired as alternative electron acceptor. So basically nitrification, denitrification are two completely different processes. Now, but they are very connected. So when we talked about ammonia oxidation, we covered first enzyme, ammonia monooxygenase, when we talked about oxygenases, but actually we did not talk specifically about ammonia monooxygenase. We talk about methane monooxygenase, which you will see later is enzyme that is highly similar and completely homolog to ammonia monooxygenase. And we used to say in field that those are actually same enzymes, and you will see why. So enzymes that participate in nitrification are first ammonia monooxygenase. So that this ammonia is aerobically oxidized to hydroxylamine by this monooxygenase, while second in line is hydroxylamine oxidoreductase or HAO. That enzyme is converting hydroxylamine to NO2 minus. So pretty much from ammonia to NO2 minus, you have two enzymes. And these two enzymes are probably the most important enzymes that we are covering in nitrification. Now, when this conversion happens from ammonia to hydroxylamine, from hydroxylamine to nitrite, 4 electrons are released and sent to the ubiquinone pool. Ubiquinone is a part of electron transport chain. Those electrons are transferred to ubiquinone through cytochromes 554 and 552. Those two cytochromes are very specific and very important for ammonia oxidation. the portion of these electrons is now returned from ubiquinone pool, and it's helping ammonia oxygenase to activate ammonia and to convert ammonia to hydroxylamine. And then you have production of NO2 minus, which is oxidized later by nitrite oxidizing bacteria to nitrate. Now, even though this is all great and aerobic, and we all heard about these processes, now we know that it's fully aerobic process. As usual, among bacteria, there is an exception, and the exception here is this organism, Nitrosomonas europaea. So it is known as ammonia oxidizer, and it performs everything what I described in this slide, ammonia oxidation and nitrite oxidation, but it does something very unusual once when it's exposed to low oxygen. So when it's exposed to low oxygen, so not completely anaerobic, just a low oxygen, we call that microaerophilic. This organism, this ammonia oxidizer, is switching its organism from already known nitrification to denitrification. So what it does is basically turning on its gene, actually enzyme near K, which is known as nitrite reductase, and this enzyme converts nitrite to nitrous oxide, and later on nitrous oxide to N2O or nitrous oxide. N2O is greenhouse gas, and that's bad for our planet. So basically, what this organism now is doing is denitrifying already produced nitrite, and that's why we call this process nitrosomonas, nitrifier denitrification. So this is very specific for this organism. It's like integration between anaerobic and aerobic metabolism. The picture here is very complicated, and don't even try to memorize it. It's just showing you how respiration or electron transport chain looks in ammonia oxidizers, just illustrating how complete denitrification happens with ammonia oxidizers and nitrite oxidizers. So, in terms of evolution of nitrogen cycle, so apparently we learned a lot about nitrogen cycle. We learned about nitrogen fixation. We learned about ammonia oxidation and nitrite oxidation and complete nitrification. We heard about denitrification as a part of anaerobic metabolism. So apparently, nitrogen cycle is quite important for development of the life on this planet, and that indicates that it definitely, and not that, like we know that microorganisms are those that actually run nitrogen cycle for us. So one of earlier suggestions was that nitrogen fixation has been developed in the early stage of evolution, and you will see probably when Nora gives a lecture, but also in later lectures, it's suggested that last universal common ancestor must be nitrogen fixator. Why, and was that really true? That's the question. So basically, components of nitrogen fixing enzymes, which is nitrogenase or denitrogenase, are iron and molybdenum, so those two cofactors, those two metals, and they were abundant on early Earth. Okay, we know that. But there is one discrepancy between this. So yes, it might be true, elements were there, but if we look the gene complexity for nitrogen fixation and how energetically demanding this is, very less likely is that nitrogen fixation was the first form of life on Earth. But then some other scientists suggested that it's possible that early nitrogenase was less efficient than the one that exists now. So what if early nitrogenase had only iron and not combination between iron and molybdenum like today's nitrogenase has? So even if nitrogenase was less efficient, if there were no denitrificants to create nitrogen gas, the level of nitrogen would drop rapidly. So that theory about less efficient denitrogenase was not possible because denitrification, when you convert NO3 minus to NO2 minus, then to NO, then to N2O, and finally to NO. So that process that we talked about in anaerobic respiration, that process is required to return the nitrogen gas into the atmosphere, but those compounds did not exist. Those organisms did not exist, so less likely that less efficient denitrogenase was correct theory. We do know that nitrogen-fixing genes are widely distributed. So I mentioned that there are like 30,000 different genes. So this is the argument that goes in the favor of early emergence of nitrogen fixation. But nitrogen-fixing genes are lacking in eukaryotic organelles. So, and we know that endosymbiotic theory is accurate. So it is not quite clear how is this happening and what was actually correct. I personally think that the first process that developed on Earth was hydrogen metabolism, and you will see in later special lecture how that happened and why I think that. But since there are no scientific evidences to confirm whether I'm right or wrong, I can only give my opinion, and the same is for you. You feel free to share opinion on this topic. I would be happy to discuss with it. But nitrogen fixation is definitely very old form of metabolism and very diverse. So if we look all together, we could agree on late emergence of nitrogen fixation and early emergence of denitrification. Again, you can be free to disagree. But it is true that only denitrification can return fixed nitrogen and sustain atmospheric nitrogen pool, which we have these days. And not all enzymes of nitrogen cycle were around during anoxic period on Earth. And we know that Earth was anoxic in the beginning. And the reason why they were not around is because there were no metal cofactors that support them. So those metal cofactors were not abundant. Enzymes that were abundant on Earth were hydrogenases. They use nickel as a cofactor, and nickel was abundant. Cytochromes, they use iron and sulfur. We know that iron and sulfur were abundant. Formate dehydrogenase that use molybdenum was abundant. Nitrite reductase, the one that can return the nitrogen gas to the atmosphere, molybdenum that uses molybdenum, that one was abundant. Enzymes of class B transition metals, the enzymes that use these metals such as copper, zinc, and cadmium were not functional because copper, zinc, and cadmium were not abundant at the time. In early anoxic Earth, as we know, ocean was very sulfidic, and sulfides reacted with transition metals, so they were not available for enzymes. So only these enzymes were available because metals that are required for their functionings were also available. Now, if copper was not available, and we know it wasn't because of because it's a transition metal that highly reacted with abundant sulfides. So if copper was not available as a redox factor, then how this nitrous oxide reductase that converts N2O to N2 operated in early Earth? Now, some theorists say that it's possible that nitrous oxide reductase was preceded, like before today's copper-based nitrous oxide reductase, there was non-copper enzyme that was lost during evolution. And then basically this non-copper enzyme was replaced by more efficient copper enzyme. And now this copper-containing enzyme that converts nitrous oxide to nitrogen was basically de novo invention of an oxic era. So those are just some of suggestions from literature that I found. Now, if we agree that denitrification was before nitrification, and we know that ammonia oxidizers and NOBs and common MOX are doing nitrification, And there are other enzymes that respire nitrate, and then they are called denitrification organisms. And we also learn now about nitrifier denitrification. We have another group of organisms that also plays a role in nitrogen cycle, but it doesn't use nitrogen in the same way and for the same purposes like nitrification organisms. So we know that AOB and AOA do nitrification, but the other organisms that perform it are methanotrophs. And we know that methanotrophs actually consume methane or single carbon compounds or hydrocarbon as a carbon source. So we would say that they do process in the same way, they do nitrification in the same way as ammonia oxidizing bacteria, but they actually do it slightly differently because they evolved these processes for different reasons. So, is there any difference in initial energy extraction between AOB and MOB? So, MOB use methane, and methane, as we know, is important for global carbon cycling. And they use methane monooxygenase that is activated by oxygen. They incorporate one oxygen into the methanol, the other one to create water. Ammonia oxidizing organisms do the same, just they incorporate one oxygen atom in ammonia and they'll build this hydroxylamine, and they also create water. So from perspective of evolution and diversity, methanotrophs are strictly highly related to nitrifiers. And they are great nitrifiers. They also are able to oxidize ammonia to hydroxylamine, but nitrifiers, on the other hand, cannot do methane oxidation. But two of them can compete for ammonia. And then you have them structured in nature based on the available resources. Now, the homology that exists between ammonia and methane monooxygenase is already confirmed. But that homology is not the only connection that apparently exists between these two organisms. However, MOB do not rely on nitrification or denitrification for growth. They only need methane for growth. While on the other hand, ammonia oxidizers do need ammonia to grow. So they do extract energy from nitrification or denitrification in case of nitrifier denitrification, but that's a separate metabolism. So the difference between MOB and AOB is in N2O oxidation. And where is the difference? How we know that? So ammonia oxidizers have the ability to use electrons from hydroxylamine oxidation via those two cytochromes that I mentioned in the first two slides to the quinone pool, and they use those electrons to drive energy production for cellular growth. During evolution, methanotrophs lost those two cytochromes, so they cannot use electrons from hydroxylamine oxidation. So there is nothing to carry those electrons to quinone pool, so they cannot grow only on ammonia, but they can assimilate ammonia as a nitrogen. And the diversity that exists in the pool of genes for nitrifying and denitrifying pathways of methanotrophic bacteria is another evidence, in addition to homology between ammonia and the methane monooxygenase, that shows tight evolutionary connection and significance of nitrifiers in global carbon cycle, but mostly methanotrophs in global nitrogen cycle. So basically the whole take point from this is that different catabolic lifestyles between AOB and MOB are undoubtful. So definitely they have different catabolisms, but they for sure have evolutionary connection that illustrates prokaryotic diversity, which was created by modular evolution of catabolism, loss of those two cytochromes in MOBs. So this would be all what I had for this lecture. So as I promised, very, very short lecture. And in my review session, you will see what is important to know and to memorize from this lecture. See you all tomorrow. Bye.